Hello, everyone. This is video 9.3. We're going to be looking at equations. Um, we sort of introduced the idea in 9.1 when we talked about the distinction between equations and expressions. But now we're going to be putting equations to work and looking at different uses of equations. So you may be thinking about equations in one or two of the ways that we're going to be talking about, but this should give you some good perspective on the various uses that we have for equations. So let's get started. So an equation, the book definition we have here is a statement of equality between two expressions. It's not a bad definition. The thing that I want you to really focus on is the equal sign. So it's a statement of equality between two expressions. So this means we're going to have an equal sign between two expressions. Now, theoretically, it could be between two or more expressions. We could have A equals B equals C, but for right now, starting off, we'll just look at two things. And even if you had A equals B equals C, you could break that down to really it's just between A and B, B and C, A and C, whatever. The point is that we have to show that there's some sort of equality, and so we have this equal sign that shows that. So if I have expression one and then expression two, we know that they have the same value. And beyond that, we know that they're interchangeable. So since they have the same value, everywhere I see expression one, I could replace it with expression two and vice versa. They're the same thing. So again, it's really important to understand and that your students understand the difference between an expression and an equation. They seem very similar. An equation is made up of expressions. Expressions go to make up an equation. Very related, very similar, but not the same thing. So one way we can use an equation is to show a calculation. And so you see here 14 plus 3 equals blank. And so we're doing nothing algebraic really in this case. Now you could argue that blank is algebraic in the sense that it's an unknown, that it represents a number from some set of numbers, so on, so on, so on. But really, at its heart, we're solving an addition problem. So while we could think of the answer as an unknown, we're not using it flexibly like a variable really. So we're just solving this answer. In this way, a lot of times students, because they've seen the equal sign in this context so much, they'll think of the equal sign as like the enter key on a calculator, or that it means like to execute something. So because this has been reinforced so much for so long for students who work with calculators too much, maybe too soon, there's a little bit of broadening out of this context, this understanding of what this equal sign really means, that it's a statement of equality, not just, like I said, an enter button. So it's a really common one for students to see, but it's sort of fraught with some misconceptions that you may have to work with. We can also use an equal sign to show identities. So this is kind of the opposite, where the first one was almost nothing algebraic at all. In this form, it's purely algebraic. So we're just showing how these symbols can be moved around to form an identity. Hopefully you recognize this as the distributive property, which is the distinction between a property and identity is not anything I really want to get into in this class, but for right now, they're statements that are both true. Um, well, enough to say that a property is something that is provably true, and an identity just means that the two things are always going to be equal to each other. So that's what we mean by an identity. I didn't want to get into it, and then I got into it anyway. That's kind of what I do. Anyway, so this is my distributive property here, and it shows this left-hand side, this right-hand side. Again, they're the same thing. They're not necessarily explicitly the same thing numerically. We're showing the same, they'll be the same thing algebraically. But if we did substitution into this, if I put numbers in for A, B, and C, then they would show numerically to be equivalent. So that's sort of the power of the algebraic expression, is that they're numerically provably true over an infinite number of cases, or at least a wide number of cases, depending on how the problem is set up. Anyway, uh, okay, so relationships. So this should be familiar from when we talked about inverse and proportional relationships. So we can use equations to show that. So the number of people. times the amount of time per person equals some fixed amount, like 60 person hours. So we've solved problems like this not that long ago. We got one person is going to take 60 hours to do a job, but now if I have two people, so 2 times what makes 60? So now the 2 people need 30 hours each. 3 people need 20 hours each. 4 people need 15 hours each. So on, so on, so on. So we have this relationship here between the number of people, the amount of time they have to work each, and the total number of person hours that need to be completed. So in this case, this equal sign shows that relationship. Lastly, the way that you've probably seen this the most, and probably the most common context you have for this is going to be in order to solve a problem, to solve an equation, quote unquote. And so something like this where we have 2 times the quantity k plus 5 equals 18, being able to solve this. This is not really the same as the first thing, which was purely numeric, and we were just finding the answer. In this case, we have a variable. We have to use our mathematical properties to isolate that variable. So there's a little bit more going on. It's a little bit more involved. Also, if you go back and look at that first problem, we're told where the answer blank is. So we're kind of given a lot of direction as to how to find that. Whereas typically in solving an equation like this, we might know to isolate the variable, but the means by which we're going to do that, the process by which we'll isolate that variable, isn't quite explicitly told as it is in a numerical problem like we saw a couple of examples ago. So these involve a little bit more thought, a little bit more problem solving skills to approach. Now I want to solve that actual problem, the 2k plus 5, I'm sorry, the 2 times the quantity k plus 5 equals 18. I want to solve this using base 10 blocks, and I want to introduce a piece into our base 10 blocks. So we have 2 of the k plus 5s equals 18. So I know how to do 5. 1, 2, 3, 4, 5. And so I know how to do 2 of those. But now I need some K pieces. And so typically what we'll do for these is that we'll just draw a block and label it as a K. Now it's important that these K pieces be, roughly the same size. This second K looks a little bit smaller. Let me fix that. So they need to be the same size because this K on the left and this K on the right have to represent the same value. So it can't be the case that the K on the left is a 4 and the K on the right is a 5. That doesn't make any sense. So if either K is 4, and that's the case for both Ks, or K is 5, and that's the case for both Ks, or whatever value it is. So this is 2 times K plus 5. So I've got one set, I have another set. And now this equals 18. And so you may see this with a line down the middle, and this line sort of represents our equality. So what's on the left and what's on the right have to be equal. You'll see this also drawn sometimes like this, where it's like a set of scales where there's sort of balance, and so then you'll see these pictures where they're like a balanced scale like this, and so again that implies that these two things have to be equal, and what you do to one side you have to do to the other. There's only about 1 million different manipulatives, models, pictures, drawings, whatever, that sort of show this equality sense of an equation. They all work, as long as you do a good job of sort of reinforcing what's going on in that model, help students make sense of it. It all works. So we've got our 18. So here's our 10. 1, 2, 3, 4, 5, 6, 7, 8. So there's a couple of different ways we can do this. And so one way I'm going to do it is we've got our 5 here and our 5 here. So we know that all together they make a long. And so these 10 pieces here and these 10 pieces here all cancel. So if this is a balance, I could remove 10 from the left and 10 from the right, and I haven't changed the balance of this problem at all. It hasn't changed anything. So now I'm down to 2k, and then these 8 over here. And so I should notice that this k could go to these 4, and this k could go to these 4, and so I see that k equals 4. And I can test this. This would be 2 times 4 plus 5, that equals 2 times 9, and that equals 18, which is my right-hand side. So it does show that this does work. I know some of you are probably thinking, why wouldn't you just divide by 2 and do k plus 5 equals 9, subtract the 5 and get k equals 4 that way? You certainly can. I've done this problem really by distributing the 2 and getting 2k plus 10 equals 18, subtracting the 10 and then dividing by 2. Both ways work. More to the point of the method of solving the problem is setting this up and introducing this k piece that we're going to start to isolate and try to find the value of that individual piece. So your method of solution may be different, and that's fine. There's not one method of solution for this. So if you did it a different way or would prefer to do it a different way, that's fine. That's not really the issue here. I do want to point out that in solving this, think about how many pieces you have to know how to do really well in order to accurately solve this sort of problem. The way that I did it, we've got the distributive property, so we have to know how to use that property. We've got understanding of place value, that those 10 blocks make the same as that one long piece. We've got division, and so we have really a partitive model of division because I have 2 Ks, so I know I have to break those 8 blocks into 2 different sets. So we're really mapping one set to each K. So there's a lot going on, and once we start to get to these points where we're synthesizing mathematical ideas together, if a student is really strong in one part but a little weak in the other part, the weaknesses start to really show through. So from a teacher standpoint, being able to look at student work and recognize, okay, this part is correct, but this part maybe isn't, and not just saying, well, you got the problem wrong. This is the idea that's maybe not quite correct, and really focusing in on where the misconceptions and the errors are. That's where you want to get to as a teacher, where you can really focus in on that sort of level of help. So let's look at a problem, one more, like 3x plus 2x minus 7 equals 3. So I want to do another problem that involves a little bit more with positives and negatives to see how that's going to work. So we've got same deal. We'll draw our line down the middle. This is our equality. So we've got an x, an x, an x, and I'm going to put these in circles so we can make the distinction between them and our units pieces. I'm going to draw them as squares anyway, just to make them distinct, but it'll just make things a little bit easier. So here's an x and here's an x, and then we've got 1, 2, 3. I was going to draw them in boxes. So here, let me fix that. 1, 2, 3, 4, 5, 6, 7, and I will draw these as little boxes. Okay, and then over here we've got 1, 2, 3. So I want to move these 7 over, or I want to move, I want to get rid of the 7. So the process by doing this, most students know, to just add 7 to both sides, but I want to really think about why we're doing it that way. The idea of like it moves over, a little cold on that idea to a certain extent, because I think it doesn't really explain why we're doing what we're doing. So we can think of this as adding 7 to both sides. So if I add these 7, we see that all of this cancels. And so then I'm going to do the same thing. 1, 2, 3, 4, 5, 6, 7. So I've added the 7 here and the 7 here. So we've kept this balanced, adding 7 to both sides. So now I've got 5 x's over here, I've got 10 over here, I'm going to do the same thing I did before. I have 5 x's, so I'm going to use my partitive model. 1, 2, 3, 4, 5. I'm going to partition this into 5 equal groups, and so I see that x equals a group of 2. And again, you could solve this, or not solve, you could substitute this back into the original equation and check and make sure. So this would be 6 plus 4 minus 7 equals 3. So that's 10 minus 7 equals 3, or 3 equals 3. This all checks out. This is all correct. Again, this is the same thing as before. A lot that we have to remember. How we combine sets, how we do addition with sets, positive and negative, so operations with integers, the additive inverse property, a lot to remember in order to solve this problem. So for your checkpoint, just like we've done the last 2 problems, let's use base 10 blocks to solve this equation. I'll let you take a run at that problem. As always, if you have any questions about this problem or anything else from this video, please be sure to let me know. All right, thanks.